Welcome back. Let's continue on chapter 11. So last time we talked about sequences and convergence of a sequence. Today we're going to talk about the increasing and decreasing sequences, generally monotonic sequences. So we say a sequence is increasing if the terms of the sequence are uh, getting larger as we go on. That means an is smaller than the an plus 1. That means the next term is larger than the one before that for all n. Meaning A1 is the smallest one, A2 would be larger than that, A3, and so on. And we say the sequence is decreasing if the opposite is true, meaning A1 is the largest value, A2 would be smaller, A3, and so on and so forth. And if one of these two happens, then we say the sequence is monotonic, which means either it's increasing or decreasing. You can have a constant sequence, is neither increasing or decreasing, because the assumption is that this is strictly less than or strictly greater than. Okay, so here a couple of examples. Let's figure out which these sequences, are they increasing or decreasing, or maybe neither. So here an equals 3 over n plus 5. Normally, if you want to find out the sequence is increasing or decreasing, try to figure out a couple of terms of the sequence. Find out what is a0. In this case, a0 would be 3 divided by, assuming n, sorry, not a0, a1, starting with 1, would be 3 divided by 6. Then a2 would be 3 divided by 7. A3 would be 3 divided by 8, and so on. So what you notice is the sequence is getting smaller and smaller. So if you can kind of suggest that this is a decreasing sequence, but the way to prove it is you have to show an is less than, an is larger than an plus 1, since you're claiming this is a decreasing sequence. And how do we find out if it's true or not? We find what is an. An is 3 divided by n plus 5, that is an. And we're going to check if this is a true statement. Is it greater than an plus 1? An plus 1 is 3 divided by, or instead of n, you have n plus 1 and plus 5. And this inequality is now the question. Is it a true statement or not? So we just need to figure out if this is a true statement. So what we do is we set up the inequality, 3 divided by n plus 5. Is it greater than 3 divided by n plus 6? And you can cross multiply, since n is always positive, greater than 1. So you can cross multiply, you'll get 3n plus 6. Is it greater than 3n plus 5? Divide both sides by 3. These two will cancel out. So what we have is, as a consequence, this implies that. This implies n plus 6 is greater than n plus 5, and you can subtract the n from both sides. You'll end up with a true statement, 6 is greater than 5. So meaning if you start with this, you can prove that, you can claim this, and backward. Which means an, this is exactly an, and this one is an plus 1. So we can kind of show that this is a true statement. So I can claim that yes, this is a decreasing sequence. The answer would be yes. Okay, how about if we look at Bn? So let's look at Bn. What was Bn? I'm going to find out a couple of terms of this sequence. B1, B1 divided by 2. B2 would be replaced 2. Then you get 2 divided by 5 would be 3. Would be 3 divided by 10. You can see that this 1/2 is larger than 2/5. 2/5 is larger than 3 over 10. This is 4 over 10. This is 4 over 10. It's larger than 3 over 10, and so on. You can continue. So what we see is that Bn is larger than Bn plus 1. And then this is a question that is it true for every n or not? Because we have to show that it is true for every n. So the question would be, is this true? So what we need to do is, again, find out what is Bn. Bn would be n divided by n squared plus 1. N divided by n squared plus 1. And we're going to find out if this is greater than Pn plus 1, which is replace n with n plus 1. N plus 1 squared plus 1. We're going to figure out if this is really a true state. And for that, we simplify it. We can cross multiply to both sides. Since the denominators are positive always, you can cross multiply, you don't need to flip the sign. So we get n times n plus 1 squared plus 1. Is it greater than n plus 1 n squared plus 1? This is a question mark. This true statement or not. So we're gonna start with there and go forward to see if we can simplify or not. So n plus 1 squared plus 1, this is simply n squared plus 2n plus 2, and multiplied by n would be n cubed plus 2n squared plus n plus 2n, and this is greater than, if you multiply the other side, you get n cubed plus n squared plus n plus 1. And you can simplify it a bit. You cross out these n cubes, you can cross out one of the n squareds, and you can cross out one of the n's. So what we end up with is n squared, I'm going to move everything to one side, plus n minus 1. Is this greater than 0 or what? Well, understandably, since n is greater than 1, this term is always larger than 1. So n squared plus n is always greater than 1. That means if you subtract 1 from it, it's always greater than 0. This is a true statement, meaning this must be true, meaning this is a true statement, meaning this is a true statement, and therefore this inequality is a true statement. So I can say, yes, this is a decreasing sequence. Yes. Okay, so normally you make a claim and try to prove it by doing this thing. And what about Cn? Here, so Cn was given as, okay, rewrite it, negative 1 to the power n divided by n. And then calculate a couple of these terms. C1 would be negative 1 divided by 1. C2 would be 1 divided by 2. C3 negative 1 divided by 3. And now you can see that C1 is less than C2. On the other side, C2 is greater than C3. It's not, because this is positive, the other two are negative. So you don't have an inequality that is going this way, or you don't go both that way. So what you have is basically this inequality structure. Whatever comes after that, we don't know. What do you notice is this is neither increasing or decreasing. So in this case, this is not monotonic. Okay, so it is kind of important to know this. And what else we're going to talk about is a bit related to this structure. Let's say if you know a sequence is decreasing, let me say, we draw it this way. Let's say we have a bunch of points that are decreasing, like that. Every time the value is small. And these values are kind of bounded below by a certain line. That means they cannot cross this line. Then what can I say about this sequence? Since it's decreasing, it should converge to something. So if we have a decreasing sequence, with a lower bound meaning that the smallest value is bounded by some number. This number is basically n. Then what we can say is that sequence would be convergent. If we don't have this lower bound, then maybe it would be decreasing, but it'll look like this. It goes on to negative infinity. So this wouldn't be an option. So without the lower bound, we can't say anything. On the other side, if we have an increasing function, something like this, you have an increasing bunch of points, and in this case, what we need is an upper bound. If we have an upper bound, means all the points are increasing, but they're getting closer and closer to some value, because they can go beyond this line. This line, we call it capital M, this largest bound possible here. Then in this case, if increasing sequence with upper bound, then what we assume, what we get is that we have a convergent sequence. Sequences converge. Otherwise, we can't say anything about it. If there is no bound, if it goes on forever, then we can say it's divergent. But if we can't find such a bound, and it's not always that easy, then we have to go through those process of figuring out if the limit does exist or not. So in this case, what we need to say is a sequence first is bounded above, or there is an upper bound above, if all the terms of the sequence is less than a certain value, in this case this n, and the sequence is bounded below, or it has a lower bound, if all the sequences terms are larger than some m value. So this m was smaller than all those values, so all the an's were larger than a in this small m. So the small m stands for lower bound and capital M for an upper bound. Okay, you don't need to find out exactly what this value is for the upper bound. You can say this must be M. There is a infimum of all those would be the convergent. Okay, so here, let's look at this example. This is a recurrence relation. A1 is given 2, an plus 1 is given 1/2 an plus 6. So let's say if we can say the sequence is bounded or not. So here, let's figure out a couple of terms of the sequence. A1 is already given, it's 2. What is A2? What would be A2? A2 would be replace A1, replace n with A1. If I replace n with 1, what you get is 1 plus 1, which is A2. So we get 1/2 A1 plus 6. And we already know what is A1. A1 is 2. So we get 1/2 2 plus 6. That is 4. So A2 would be 4. And how about A3? A3 would be 1/2 A2 plus 6. And that would be 1/2 4 plus 6, which is 5. And if we continue, A4 would be 1/2 5 plus 6, 11/2. And A5, I just want to calculate a couple of them just so you can see the structure. 1/2 11/2 plus 6, that would be 12/23/4. Okay, you kind of notice something. These numbers are getting closer and closer. 23/4 is closer and closer to 6. 11/2 is 5.5. This is like 5.75. So I can say these numbers are getting closer and closer to 6. I'm not sure if it's going to be larger than 6 or not, but I can kind of create that claim similar to what I did for increasing or decreasing. So I can claim that this an, this is what I claim. I claim that an is less than 6. Less than or equal. How can I show it? So can I prove it? what I can do is I can say, let's say an is less than 6. How about an plus 1? Is that going to be less than 6 as well? Because if I can show that, then I can say definitely this an plus 1, then definitely I can say for every n this is true. If I start with a smaller number less than 6 and I continuously doing this recurrence relation, but I'm proving that at every step I still have a number less than 6. So let's try that. If I assume that an is less than 6, what is an plus 1? An plus 1 would be 1/2 an plus 6, which means it is 1/2, which is less than or equal to 1/2, because I'm going to replace an with 6. 6 plus 6, and that is exactly 6. So what I kind of showed is that the next entry, the next term of the sequence is always also less than 6. And this tells you that if you start with a term that is less than 6, what you end up with is that the next term would be also less than 6. So if you continue with this process, you're going to be always, the next entry would always be less than 6. So did I prove it? Yes, I showed that an is always less than 6 for all n. Okay, so I found the bound. And if I show that, if I say that it is bounded, and by the way, this is an increasing sequence. You notice that the sequence is increasing 2, 4, 5. So I kind of expect this structure. If you have an increasing sequence, less than 6, in this case, maybe less than 7 if you want. Doesn't really matter what the upper bound is. In this case, I pick 6. If it's less than 6, then you want to show that there is a limit. Is it 6 the limit, or maybe a smaller number is the limit? So how do we find the limit? So is an find, how about I say, find the limit as n approaches to infinity of a. Now here's the issue. It's not that easy because we don't have a specific formula for a. What we have is a recurrence relation. So how do we find the limit? In these cases, when you're dealing with limit, if for recurrence relation, what you should think of is if n approaches to infinity, and this guy approaches to L, what happens for an plus 1 as n approaches to infinity? What do you expect? If this is true for every n after a certain value, then this must also approach to L. Because infinity plus 1 really doesn't make any difference. So I can claim that as you're calculating the limit for n approaching to infinity, an and an plus 1, they both have to approach to the same value. Because they're very close to it. You can kind of claim that these two are both very close to that L value. So I can say in the sequence that we had, I'll write it, limit an plus 1 was equal to 1/2 an plus 6 as n approaches to infinity. This is true. That means an plus 1, which is the limit of that would be L, must be equal to 1/2 L plus 6. And you can kind of solve this equation. This is a linear equation. You get 2L equals L plus 6. Therefore, you can find out what is L. So if you continue this procedure, what you expect at the end is that the limit of the sequence would be 6. So I have a convergent sequence where the limit is simply 6. Okay, here's another example for upper and lower bound, by the way. You don't always have to find the closest upper and lower bound. So in this case, what I can say is e to the power negative n. So here an, you can calculate some values to see how it looks like. 3 minus 2 e to the power negative 1. It's not that easy to see how this number looks like, but if you have an idea of how e looks like, e to the power x would have looked like this. E to the power n would have looked like some points like this. Starting there, so you'll have a bunch of points. If you change it to negative, what you would have is basically that. And this is e to the power negative n. As n is increasing, sorry, not this way, the other way. E to the power negative n would look like something like this, because the negative was the other side, sorry. As n is increasing, then you would have, what do you have? You would have, this is negative e to the power negative. These bunch of points, there we go. You have to do double reflection. This is e to the power x, negative e to the power x would be, okay, e to the power negative x looks like this. And negative e to the power negative x would just be flipped around, and you only care about the positive x value, so we don't care really about negative. That's why I only looked at this part. So what you can see is that e to the power negative n is kind of bounded, and negative e to the power negative n is also bounded. So I can say this part is bounded by an upper line which is 0. So here 2 times that would still be bounded, and then if I add 3 to it, I can still say it's bounded. So what I'm claiming that is that I always have this term. I'm saying that e to the power negative n is always less than 0. That's what I'm claiming by graphically showing you. And then 2 times that, which is negative 2 e to the power negative n, is still less than 0. If you add 3 to it, 3 minus 2 e to the power negative n would be less than 3. That's what I'm claiming. So I kind of say that there is an upper bound, and that upper bound is 3. You can see it graphically that if I have this graph and multiply it by 2, it will look like a bunch of points. It would look like this. This would be 2, negative 2 e to the power negative n. If you add 3 to it, it will be just shifted up, and it will look like something like this. This line is 3. Okay, so what I found that this is an is bounded above. It's not always a fixed strategy. You have to come up with strategies for different cases. And what I can say is I can find the convergence. So that means you have a bounded above sequence. In this case, it's an increasing sequence. So I can say it is convergent. So an is increasing. You can calculate and show that it is increasing. Therefore, there is convergence. So I can calculate the limit. Limit an as n approaches to infinity would be limit 3 minus 2 e to the power negative n as n approaches to infinity. This one is quite easy because this term, as n approaches to infinity, approaches to 0. Graphically, you should see it, and you can always write this 1 over e to the power n. As n approaches to infinity, that still would be 0. So you have 3 minus 2 times 0, which is 3. So we found the convergence, the limit of the sequence. Okay, this is kind of how you show, if you're given the information by boundedness and monotonic behavior, how you can claim that is a convergence or divergence for sequences. Okay, so this is it for this section. I'm gonna stop here.